Hi, my name is David Hunter. Today I'd like to work through a problem that's an intermediate microeconomic problem on utility maximization. Here's the question. Suppose you have two goods, X and Y, and your income is $200, and the price of good X is $4, and the price of good Y is $2. Question is, to find the utility maximizing choice of X and Y, assuming your utility is in the form of a Cobb-Douglas utility function, particularly that utility is equal to X to the 1/2 times Y to the 1/2. After you've solved for X and Y, be sure to graph your answer in a well-labeled graph. Let's first start by taking a look at the general solution to utility maximization problems. We're actually going to use the budget constraint for this problem. So here's the data for the budget constraint. We have income and prices. And if we have the graph of good X and Y, you'll notice that if we spend all of our income on good Y, the $200 is enough to buy 100 units of good Y if the price of Y is 2. That's 200, our income, divided by 2, the price of good Y, gives us 100. Similarly, if we spend all of our income on good X, 200 divided by 4 gives us 50 units of good X. If we join these 2 points together, we get the budget constraint. Notice that the slope of the budget constraint in absolute value terms is 2. You can calculate that explicitly from the numbers in the graph. In other words, the change in Y is 100 divided by the change in X of 50. 100 divided by 50 is 2. Or you can use the fact that the price ratio, Px divided by Py, always gives you the absolute value of the slope of the budget constraint. That price ratio is known as the relative price of good X in terms of good Y. So 2 is the number of units of good Y that you have to spend in order to buy 1 unit of good X. Now let's draw in some indifference curves. And I've drawn in 3 indifference curves, but there are indifference curves that span the entire space, all the different combinations of X and Y that you can assume. That means that every point can be compared to any other point, and we always know if the points are on the same indifference curve, in which case you're indifferent between those 2 points, or the higher the indifference curve is, the greater the utility you get from that combination of good X and Y. What else do we need to know? Well, we need to know that the absolute value of the slope of the indifference curve is known as the marginal rate of substitution, MRS for short, and that's equal to the ratio of marginal utilities for good X to good Y. Now, if we're taking a look, there are 3 kind of possible points that we can compare, A, B, and C. Which of these 3 points gives us the highest level utility? Well, that's point C. But is that our utility maximizing point? No, because we cannot afford point C. In fact, the 2 points that we can't afford are points A and B. Now, which of these 2 points gives us the highest possible utility? And that you can see is point B, because the point B is on the highest possible indifference curve. So our solution is to choose points X and Y such that, number 1, the tangency condition holds. The tangency condition is that the slope of the budget, or rather the slope of the indifference curve, is equal to the slope of the budget constraint. Now, I always like to phrase that in absolute value terms. So the marginal rate of substitution, that's the absolute value of the slope of the indifference curve, is equal to the price ratio, which is the absolute value of the slope of the budget constraint. So those 2 things have to be equal, but we also need the budget constraint condition holding, which means that we have to be spending all of our income. Now we're ready to solve this problem. Let's start by calculating the marginal rate of substitution. As you recall, the utility function was X to the 1/2 times Y to the 1/2, and the marginal rate of substitution is the ratio of marginal utility of good X to the marginal utility of good Y. Let's calculate first the marginal utility of good X. That's the partial derivative of utility with respect to good X. And that means we take the derivative of the utility function with respect to X, holding all other variables constant. So the X to the 1/2, if we took the derivative of that, we just apply the exponent rule. The 1/2 exponent for good X, that comes down to the front. Then we subtract off 1 from the exponent. So 1/2 minus 1 gives us x to the negative 1/2. Y to the 1/2 just comes along because that's considered to be a constant. The same applied to the marginal utility of good y, gives us the partial derivative utility with respect to y. So the 1/2, the exponent of good y, comes down to the front. X to the 1/2 is just a constant that comes along. And then we have y to the negative 1/2, which we get by subtracting 1 from the exponent of good y. Now the ratio of these two things is actually just y over x. And you can see that we get that by just dividing the top marginal utility of good x by the marginal utility of good y. The 1/2s cancel. And then if we look at the term, the x term, we can use this rule here that x to the a divided by x to the b is equal to the x to the a minus b. So in this particular case, we have a, that's the exponent of the top term, is equal to negative 1/2, and b, the exponent of the bottom x, is equal to 1/2. So negative 1/2 minus 1/2 gives us negative 1 as the exponent to x, and we know that x then minus 1 is the same as 1 over x, so that's how we get the x on the bottom. Doing the same for the y term, we have y to the 1/2 divided by y to the negative 1/2, so the exponents are 1/2 minus a negative 1/2, which is the same as 1/2 plus 1/2, which gives us y to the first power, which gives us the top term. Now let's continue on to the tangency condition. Recall that the tangency condition was that the marginal rate of substitution is equal to the price ratio. Well, the marginal rate of substitution is just y over x. The price ratio, 4 divided by 2, is 2. So if we simplify this little equation, we get y is equal to 2x. The next step involves the budget constraint condition. We just showed that y is equal to 2x. That was a result of the tangency condition. Now we'll just go ahead and plug that into the budget constraint condition. Here's the budget constraint. 4x plus 2y is equal to 200. Now, instead of y, we're going to plug in 2x for y. That gives us ultimately that 8x is equal to 200. And that simplifies to x is equal to 25. When we plug x equals 25 into the top equation, then we get y is equal to 50. That is our utility maximizing choice of x and y. And finally, let's go ahead and graph the solution. If you recall, we solved for the utility maximizing choice of x and y. X star was 25 and y star is 50. Let's draw the graph for x and y. We'll put in budget constraint. Here's our label for it. Now let's draw in our difference curve. Point A, that represents the point that solves the utility maximizing problem. At point A, both conditions, the tangency condition and the budget constraint condition, are met. And point A determines that the optimal choice for good y is 50, the optimal choice of good x is 25. And there you have the solution. I hope you found this video helpful. Thank you so much for watching.